There are things the universe will not allow. Not because our technology is too primitive, not because we haven't figured out the right equation yet, but because the laws of physics themselves say no. And these aren't soft limits. They aren't barriers waiting to be broken by some future genius or some civilization a million years ahead of us. These are unbreakable walls imposed by reality itself. Walls that cannot be climbed, tunneled through, or wished away. Tonight, we're going to explore the boundaries that physics cannot cross. The places where the universe draws a line and says, this far and no further. And by the end, you're going to realize the cage we live in is far stranger than you ever imagined. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. But for now, make yourself comfortable. Let's begin. Let's start with something you already believe. Speed limits are meant to be broken. Humans have been breaking them for as long as humans have existed. For most of our history, the fastest any person could travel was the speed of a running horse. About 40 miles per hour on a good day, with a strong animal on flat ground. That was it. That was the ceiling for tens of thousands of years. Every army, every messenger, every fleeing refugee moved at roughly the same speed. The speed of a horse. Then we built trains. Suddenly, humans could move at 60, 70, 80 miles per hour. People thought it was dangerous. Some doctors in the 1800s genuinely worried that the human body couldn't survive speeds above 30 miles per hour. They thought our organs might shift inside us, or that we'd suffocate from the air rushing past. They were wrong. We went faster. By the early 1900s, automobiles were reaching speeds over 100 miles per hour. Then came aircraft. In 1947, Chuck Yeager broke the sound barrier in the Bell X-1, flying faster than 760 miles per hour. People had said that was impossible too. They called it a wall, the sound barrier. They thought aircraft would shake themselves apart as they approached the speed of sound. They were wrong again. We pushed through it and kept going. In 1969, Apollo 10 reached a speed of about 24,791 miles per hour during its return from the moon, making it the fastest crewed vehicle in history. The Parker Solar Probe, launched in 2018, has reached speeds exceeding 430,000 miles per hour as it swings close to the sun, making it the fastest object humans have ever built. Every single time someone said there was a speed limit, we broke it. Every barrier turned out to be an engineering challenge, not a fundamental wall. So here's the question that seems obvious. Why should the speed of light be any different? Why can't we just build something faster? Build a bigger engine, use more fuel, push a little harder. Surely it's just a matter of time before we break this barrier too, the way we broke all the others. The answer is going to challenge everything you think you know about speed, about space, and about the very nature of reality. Because the speed of light is not like the sound barrier. It's not like any barrier we've ever encountered. It's not an engineering problem. It's not a wall made of something that you can break through with enough force. It's something much deeper. Something much stranger. Something woven into the actual structure of the universe itself. The speed of light is exactly 299,792.458 kilometers per second. Not approximately, exactly. This number is so fundamental that in 1983, scientists actually redefined the meter based on it. 1 meter is now officially defined as the distance light travels in 1,299,792,458 of a second. We didn't measure the speed of light and get a number. We fixed the speed of light and redefined our units of measurement around it. That's how fundamental it is. But here's the thing, most people don't understand. The speed of light isn't special because light happens to travel at that speed. Light travels at that speed because that speed is special. It's built into the geometry of space-time. It would exist as a cosmic speed limit even if light didn't exist at all. It's the speed at which cause and effect propagate through the universe. The speed at which any influence, any force, any information can travel from one point to another. Light just happens to be one of the things that travels at this maximum speed, because light has no mass and therefore naturally moves as fast as anything can possibly move. This distinction matters enormously. When people hear speed of light, they think of it as a property of light, a feature of photons, but it's not. It's a property of space-time, a feature of the universe. Light doesn't define the speed limit. The speed limit defines how light behaves. And this idea didn't come out of nowhere. It came from one of the most famous failed experiments in the history of science. In 1887, 2 American physicists, Albert Michelson and Edward Morley, set out to measure something that everyone assumed must exist: the luminiferous ether. At the time, physicists believed that light, like sound, must travel through a medium. Sound moves through air. Ocean waves move through water. Light, they assumed, must move through some invisible substance that filled all of space. They called it the ether. And since the Earth is moving through space as it orbits the Sun, it should be moving through this ether. That means light traveling in the direction of Earth's motion should appear slightly slower, and light traveling perpendicular to it should appear slightly faster. The difference would be tiny, but measurable with the right equipment. Michelson and Morley built an extraordinarily sensitive device called an interferometer, capable of detecting differences in the speed of light as small as a few kilometers per second. They ran the experiment. They rotated their apparatus. They repeated it at different times of day and different times of year as the Earth changed direction in its orbit. The result was nothing. Absolutely nothing. The speed of light was identical in every direction, regardless of the Earth's motion. There was no ether wind, no detectable medium. The speed of light appeared to be the same for everyone, no matter how they were moving. This was baffling. It contradicted everything physicists thought they knew about how waves behave. The result sat like an unexplained anomaly for nearly 2 decades, until a 26-year-old patent clerk in Bern, Switzerland, realized that the experiment hadn't failed at all. It had revealed something fundamental about the universe. To understand why this speed limit is absolute and unbreakable, you need to understand what Albert Einstein figured out in 1905, when he was just 26 years old, working as a patent clerk in Bern, Switzerland. Einstein wasn't thinking about speed limits. He was thinking about a puzzle that had been bothering physicists for decades. The puzzle was this: when you measure the speed of light, you always get the same answer. It doesn't matter if you're moving toward the light source or away from it. It doesn't matter if the light source is moving toward you or away from you. The speed of light is always the same. Always 299,792 kilometers per second. In everyday life, speeds add up. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the platform sees the ball moving at 70 kilometers per hour. That's intuitive. That's obvious. That's how speed works, except it isn't. Not when you get close to the speed of light. If you're on a spacecraft moving at half the speed of light and you shine a flashlight forward, you might expect that someone standing still would see the light moving at 1.5 times the speed of light. Half the speed of light from the ship, plus the full speed of light from the flashlight. But that's not what happens. The person standing still sees the light moving at exactly the speed of light. Not 1.5 times, exactly 1 times, the same speed. This seems impossible. It seems like a contradiction. How can the light be moving at the same speed for both observers when one of them is already moving at half the speed of light? Something has to give. And Einstein realized what gives: space and time themselves. Einstein's theory of special relativity showed that space and time are not fixed, rigid, absolute things. They're flexible. They bend and stretch depending on how fast you're moving. When you move very fast, close to the speed of light, 2 strange things happen. First, time slows down for you relative to someone who isn't moving. This is called time dilation. Second, distances in the direction you're moving actually shrink. This is called length contraction. These are not illusions. They are not tricks of perception. They are real, physical changes in the passage of time and the measurement of distance. And they happen in exactly the right way to ensure that everyone, no matter how fast they're moving, always measures the speed of light as the same value. The universe literally adjusts space and time to keep the speed of light constant. If you could actually ride aboard a spacecraft accelerating toward the speed of light, the visual experience would be profoundly alien. As your speed increases, the light from stars ahead of you would be compressed to shorter wavelengths through relativistic Doppler shifting. White stars would turn blue, then ultraviolet, eventually shifting beyond the range of human vision entirely. Meanwhile, stars behind you would stretch to longer wavelengths, reddening, then dimming into infrared, then disappearing. And something stranger still would happen. A phenomenon called relativistic aberration would cause the starlight from all directions to bunch together ahead of you, as if the entire universe were being funneled into a shrinking circle directly in front of your ship. Stars that were beside you, even behind you, would appear to migrate forward, crowding into an ever tighter disk of blinding, blue-shifted light ahead. Behind you, darkness. The universe would look like a tunnel, a blazing ring of compressed starlight in front of you and absolute void behind. This isn't artistic speculation, it's a direct, calculated consequence of special relativity. The universe would literally look different because space and time are being distorted by your motion. Think about that for a moment. The universe doesn't care about keeping your measurements of distance the same. It doesn't care about keeping your experience of time the same. The one thing it absolutely insists on preserving, The one quantity that must remain identical for every observer in every circumstance is the speed of light. That's how fundamental this number is. Space and time bend to protect it. Now, this has a consequence that ruins any hope of breaking the light speed barrier. As an object with mass accelerates, it gets harder and harder to accelerate further. This isn't because of friction or air resistance or any external force. It's because the object's inertia increases as it approaches the speed of light. The faster it goes, the more resistant it becomes to further acceleration. And this resistance doesn't just increase gradually, it increases without limit. If you plot the energy required to accelerate an object as a function of its speed, the curve goes up slowly at first. At everyday speeds, the increase is negligible. You'd never notice it driving a car or flying a plane. Even at a significant fraction of the speed of light, the increase is manageable. But as you approach the speed of light, the curve shoots upward toward infinity. At 90% of light speed, you need about twice the energy you'd expect from everyday physics. At 99%, you need about 7 times as much. At 99.9%, about 22 times. At 99.99%, about 71 times. And it keeps climbing, faster and faster, approaching infinity as you approach the speed of light. To actually reach the speed of light, you would need infinite energy. Not a lot of energy. Not an impractical amount of energy. Infinite energy. And infinite energy doesn't exist. There isn't enough energy in the entire observable universe to accelerate a single grain of sand to the speed of light. Not even close. The observable universe contains an enormous but finite amount of energy, and finite will never equal infinite, no matter how large it gets. This is why the speed of light is different from every other speed barrier we've broken. The sound barrier was tough, but it just required more thrust. Escape velocity was challenging, but it just required bigger rockets. These were engineering problems with engineering solutions. The speed of light is a mathematical impossibility. It's like asking someone to count to infinity. You can keep counting higher and higher, but you'll never reach it. Not because you're counting too slowly, but because infinity isn't a number you can arrive at. This isn't just theory. This has been tested experimentally with extraordinary precision over and over again for more than a century. The evidence is overwhelming. At CERN, the European Organization for Nuclear Research, particles are accelerated to incredible speeds inside the Large Hadron Collider. Protons in the collider reach 99.999991% of the speed of light. That's 7 nines after the decimal point. The collider uses enormous amounts of energy to push these protons faster and faster. But no matter how much energy is poured in, the protons never reach the speed of light. They get closer and closer, each tiny increment requiring vastly more energy than the last, but they never touch it. They asymptotically approach it, like a curve that gets closer and closer to a line, but never actually reaches it. Time dilation has been measured directly. In 1971, physicists Joseph Haffel and Richard Keating placed atomic clocks on commercial airplanes and flew them around the world. When they compared these clocks to identical clocks that had stayed on the ground, the flying clocks had lost time. Not much, just a few hundred nanoseconds, but exactly the amount predicted by Einstein's equations. time literally passed more slowly for the clocks that were moving. This experiment has been repeated with far greater precision since then, and the results always match relativity's predictions. GPS satellites provide another confirmation that you interact with every single day without realizing it. The atomic clocks on GPS satellites run at a slightly different rate than clocks on the ground. This is partly because the satellites are moving fast, which slows time down due to special relativity, and partly because they're farther from Earth's gravitational field, which speeds time up due to general relativity. If the GPS system didn't account for these relativistic effects, your position readings would drift by about 10 kilometers per day. The fact that GPS works at all, that it can pinpoint your location to within a few meters, is proof that Einstein's relativity is correct. Every time you use a map on your phone, you're relying on the reality of time dilation. Muons provide yet another confirmation. Muons are subatomic particles created when cosmic rays hit the upper atmosphere. They have a very short half-life, about 2.2 microseconds. At this decay rate, even traveling at nearly the speed of light, muons created at the top of the atmosphere should decay long before they reach the ground. The math is straightforward. At their speed, they should only travel about 660 meters before half of them decay. But the atmosphere is much thicker than that. The muons are created about 15 kilometers up. Yet we detect enormous numbers of muons at ground level. Why? Because from our perspective, the muons are moving so fast that time dilation extends their lifetime. Their internal clock runs slower relative to ours. What seems like 2.2 microseconds to the muon is much longer from our point of view. Long enough for them to reach the ground before decaying. And from the muon's perspective, length contraction shrinks the distance to the ground. Both explanations are valid. Both are real. And both confirm Einstein's relativity. Now, I know what some of you are thinking. What about warp drives? What about wormholes? What about all those clever ideas from science fiction that supposedly let you get around the speed limit without technically breaking it? Let's address these because they come up every time someone talks about the speed of light, and the reality is more complicated and more disappointing than most people realize. The Alcubierre warp drive was proposed in 1994 by Mexican physicist Miguel Alcubierre. The idea is elegant. Instead of moving a spacecraft through space faster than light, you contract the space in front of the ship and expand the space behind it. The ship itself sits in a bubble of flat space and doesn't actually move faster than light locally. But the bubble itself moves through space, carrying the ship with it at effectively faster than light speeds. It's like standing on a moving walkway at an airport. You're not walking any faster, but the ground beneath you is carrying you forward. On paper, the Alcubierre drive is a valid solution to Einstein's field equations in general relativity. It's mathematically consistent, but mathematics and physical reality are not the same thing. The Alcubierre drive requires something called exotic matter. Matter with negative energy density. In normal physics, energy is always positive or zero. Exotic matter would have less than zero energy, which is a concept that most physicists consider deeply problematic at best and physically impossible at worst. Some quantum effects, like the Casimir effect, produce tiny regions of negative energy density under very specific conditions, But these effects are far too small to be useful for a warp drive. You'd need enormous quantities of exotic matter, and there's no known way to produce it in the amounts required. Early calculations suggested you'd need more negative energy than the total positive energy in the observable universe. Later refinements brought this number down, but it's still astronomical, far beyond anything we could conceivably produce. And there are deeper problems. Several physicists have shown that the Alcubierre drive would create horizons around the bubble that would prevent anyone inside from controlling it. You couldn't turn it on, steer it, or turn it off from inside the bubble. You'd need to set up the entire warp field in advance from outside the bubble, which defeats much of the purpose. Others have shown that the front of the bubble would accumulate high-energy particles during transit, releasing them in a catastrophic burst upon arrival. You'd essentially arrive at your destination accompanied by a lethal blast of radiation. Wormholes are another popular idea. A wormhole is a theoretical shortcut through space-time, a tunnel connecting two distant points. If wormholes existed and could be traversed, you could potentially step through one and emerge thousands of light years away in an instant. The concept comes directly from general relativity. Einstein himself, along with the Nathan Rosen, described these structures in 1935. They're sometimes called Einstein-Rosen bridges, but the Einstein-Rosen bridges that arise naturally in the mathematics of general relativity are not traversable. They pinch off and collapse far too quickly for anything to pass through them. Keeping a wormhole open long enough to travel through it would require, once again, exotic matter with negative energy density. And even if you could somehow keep one open, the wormhole would be inherently unstable. The slightest perturbation, even a single photon entering the mouth, would cause it to collapse. Furthermore, both warp drives and wormholes run into a devastating problem. Because it turns out that breaking the speed of light doesn't just mean going fast. It means breaking something far more fundamental. If you can travel faster than light by any means, whether by breaking the light speed barrier directly or by taking a shortcut through space-time, you can effectively travel backward in time. This isn't speculation. It's a straightforward consequence of the mathematics of special relativity. And traveling backward in time creates paradoxes so severe that many physicists believe the universe simply does not allow it. As for tachyons, hypothetical particles that travel faster than light, they remain purely theoretical. No tachyon has ever been detected. And if tachyons did exist, they would have imaginary mass, a concept that doesn't correspond to anything in unobserved reality. Tachyons would also violate causality, allowing effects to precede their causes, which brings us right back to the paradox problem. The universe seems to have a deep commitment to preventing faster than light travel, and every theoretical loophole we found has turned out to have a catch that makes it unworkable. Only massless particles can travel at the speed of light. Photons, the particles of light, have no rest mass. They don't need to be accelerated to light speed. They're born at that speed, and they always travel at that speed. They cannot slow down or speed up. A photon emitted by a distant star travels at exactly the same speed as a photon emitted by your desk lamp. A photon in a vacuum always moves at 299,792.458 kilometers per second. This is simply what photons do. It's their nature. From the photon's perspective, if we could somehow adopt the perspective of a massless particle, something strange happens. Time doesn't pass. At all. For a photon, the moment of emission and the moment of absorption are the same moment. A photon that left a galaxy 13 billion years ago and just now enters your telescope experienced no time during that journey. From its perspective, it was emitted and absorbed simultaneously. The entire trip, 13 billion years from our point of view, was instantaneous from the photon's point of view. This is the extreme limit of time dilation. As you approach the speed of light, time slows down. At the speed of light, time stops. Beyond the speed of light, time would reverse, which is part of why the universe doesn't allow it. What does all this mean for us? It means the distances between stars represent something more than just empty space to be crossed. They represent time that must be spent. The nearest star beyond our Sun, Proxima Centauri, is about 4.24 light-years away. Even if we could build a spacecraft that traveled at 90% of the speed of light, a speed that will require more energy than any civilization has ever produced, the trip would still take over 4 years from Earth's perspective. At 99% of light speed, time dilation would mean the travelers would experience only about 7 months. But people on Earth would still wait over 4 years for them to arrive. Push this further, and the consequences become emotionally staggering. At 99.9999% of the speed of light, time dilation becomes extreme. A traveler could cross the entire Milky Way galaxy in what feels to them like a few hundred years. But when they arrive, 100,000 years will have passed back on Earth. Everyone they ever knew, every civilization that existed when they left, will be ancient history. Dust. This is the twin paradox made real. Not a paradox at all, actually, but a confirmed prediction of special relativity. Time genuinely passes at different rates for people in different states of motion. The traveling twin really does age less. The universe doesn't owe you synchronization, and it doesn't give it. And that's just to the nearest star. Most stars in our galaxy are thousands of light years away. The galaxy itself is 100,000 light years across. Even at the speed of light, crossing our galaxy would take 100,000 years. Other galaxies are millions or billions of light years away. The distances are so vast that even at the absolute maximum speed the universe allows, they translate into travel times longer than human lifetimes, longer than civilizations, longer than species. This is not a temporary problem waiting for a technological solution. This is a permanent feature of the universe. The speed of light sets a fundamental limit on how fast anything can travel, and by extension, on how quickly anything can happen. It limits the spread of information, the reach of influence, the pace of communication, and the boundaries of what any civilization can hope to achieve in a given span of time. But here's what makes this even more profound, and what makes this limit so much deeper than it first appears. The speed of light isn't really about light at all. It's about causality. It's about the relationship between cause and effect. The speed of light is the speed at which causation itself moves through the universe. When something happens at one point in space, the effects of that event spread outward at the speed of light, not faster. They cannot spread faster because there is no faster. The speed of light is the universe's maximum refresh rate, the fastest that any change can ripple through reality. And this means the speed of light doesn't just limit how fast you can travel, it limits what you can influence. It limits what you can know. It limits what can possibly affect you. It draws a boundary around every event in the universe, separating what can be connected from what must remain forever separate. That boundary, that deeper structure, is what makes the speed of light so much more than a speed limit. Because when you start to understand what causality really means, and what happens when you try to break it, the universe reveals a prison far stranger and far more absolute than a simple speed limit. There's something so obvious about the way the universe works that most people never stop to think about it. Causes come before effects, always, without exception. You drop a glass and then it shatters on the floor. You strike a match and then it bursts into flame. You speak a word and then someone across the room hears it. The cause happens first. The effect follows, never the other way around. The glass doesn't reassemble itself and leap back into your hand. The match doesn't unlight. The sound doesn't travel backward into your mouth. The arrow of causation always points in one direction, from past to future, from cause to effect. This seems so obvious that it barely seems worth stating. Of course, causes come before effects. How could it be any other way? But here's what most people don't realize. This ordering, this structure where causes always precede their effects, is not guaranteed by some abstract philosophical principle. It's enforced by a physical mechanism. And that mechanism is the speed of light. The speed of light isn't just a speed limit for rockets and radio signals. It's the speed of causality itself. It's the maximum rate at which any cause can produce any effect anywhere in the universe. And this creates a structure in space-time that is so rigid, so fundamental, that it literally defines what it means for events to be connected. To understand this, you need to understand one of the most important concepts in all of physics: the light cone. Imagine you're standing in a dark room and you turn on a light bulb. The light expands outward from the bulb in all directions at the speed of light. After 1 second, the light has formed a sphere around you with a radius of about 300,000 kilometers. After 2 seconds, the sphere has a radius of 600,000 kilometers. After a year, the sphere has a radius of 1 light year. If you drew this expansion on a diagram with space on the horizontal axis and time on the vertical axis, the light would trace out a cone shape. The edges of the cone expand outward at exactly 45 degrees, representing the speed of light. This is your future light cone. Everything inside this cone, every point in space and time that the light can reach, represents an event that you could potentially influence. If you wanted to send a signal, throw a rock, or exert any kind of influence on an event inside your future light cone, you could do it. The signal or the rock or whatever you send would travel at less than the speed of light, which means it stays inside the cone. It reaches the event before or at the moment the event occurs, and causation works normally. You did something, and it had an effect. Now imagine reversing the direction. Instead of looking at where your light can go, look at where light could have come from to reach you right now. Draw another cone, this time pointing backward in time. This is your past light cone. Everything inside this cone represents an event that could have potentially influenced you. If something happened inside your past light cone, there was enough time for a signal traveling at the speed of light or slower to reach you. That event could have been a cause of something you're experiencing right now. Your past light cone contains everything that could have caused your present. Your future light cone contains everything that your present could potentially cause. These two cones together define the structure of causality for your location in space-time. But here's the critical part. Everything outside both cones, every event that is neither in your past light cone nor in your future light cone, is causally disconnected from you. These events are too far away in space and too close in time for any signal, even one traveling at the speed of light, to connect them to your present. You cannot influence them. They cannot influence you. There is no possible cause and effect relationship between you and those events. Not because of any practical limitation. Not because your technology isn't good enough, but because the geometry of space-time literally does not allow it. This is not an abstract theoretical idea. It has real, measurable consequences. When the sun emits a solar flare, the radiation from that flare takes about 8 minutes and 20 seconds to reach Earth. During those 8 minutes and 20 seconds, the flare and Earth are causally disconnected. The flare has happened, but as far as Earth is concerned, it hasn't happened yet. Nothing on Earth can react to the flare because no information about the flare has arrived. The flare is outside Earth's past light cone for those 8 minutes. Only when the light from the flare reaches Earth does the event enter our past light cone, and only then can it have any effect on us. Now, in everyday life, this doesn't matter much. Light is so fast, and the distances in our daily lives are so small, that cause and effect appear to be instantaneous. When you flip a light switch, the delay before the light reaches your eyes is about a billionth of a second. You'd never notice it. For all practical purposes, the cause and the effect are simultaneous. But as distances increase, the delay becomes significant. And in the vastness of space, this delay becomes the dominant fact of existence. A command sent to a rover on Mars takes between 3 and 22 minutes to arrive, depending on the planet's positions. A signal to Voyager 1 takes nearly a full day. A hypothetical message to Proxima Centauri would take over 4 years. And these delays are not just inconveniences. They represent a fundamental truth about the structure of reality. Cause and effect are separated not just by distance, but by time. And the speed of light determines exactly how much time. Now, here's where things get truly strange. And truly frightening. Everything I've just described depends on one critical assumption: that nothing travels faster than light. As long as all signals, all particles, all influences are confined to the interior of the light cone, causality works perfectly. Causes always precede effects. The ordering of events is consistent for all observers. The universe makes sense. But what happens if something could travel faster than light? What if you could send a signal or move an object outside the light cone? The answer is devastating. If faster than light travel or communication is possible, then the ordering of cause and effect breaks down. Events that one observer sees as cause followed by effect would be seen by another observer as effect followed by cause. And this isn't a matter of perception or illusion. Both observers would be equally correct. The ordering of events is not absolute for events separated by faster than light intervals. It depends on who's watching. To understand why, you need to know something strange about special relativity. Different observers moving at different speeds don't agree on which events are simultaneous. This is called the relativity of simultaneity, and it's one of the most counterintuitive aspects of Einstein's theory. If I'm standing still and two firecrackers go off at the same time, one to my left and one to my right, I say they were simultaneous. But someone riding past me on a fast-moving train might see the firecracker on the right go off first, and the firecracker on the left go off second. And someone riding in the opposite direction might see the left one go off first. All three of us are correct. There's no absolute fact about which firecracker went off first. Simultaneity is relative. There's a thought experiment that makes this vivid. Imagine a pole that's 20 meters long and a barn that's only 10 meters long. Now imagine the pole is moving through the barn at a significant fraction of the speed of light. From the barn's perspective, the pole is length contracted. It's shorter than 10 meters. It fits inside the barn with room to spare. You could, in principle, briefly close both barn doors simultaneously, with the pole entirely inside. But from the pole's perspective, it's the barn that's length contracted. The barn is shorter than 10 meters, and the 20-meter pole never fits inside it. Both descriptions are correct. Whether the pole fits inside the barn depends on who's asking. The two barn doors don't close simultaneously in the pole's frame. Simultaneity is different for each observer. This isn't a trick. It's the actual geometry of space-time at high speeds. For events inside each other's light cones, this doesn't cause problems. Even though different observers might disagree about the time between two causally connected events, they all agree on the order. If event A causes event B, every observer sees A happen before B. The mathematics of special relativity guarantees this, but only as long as the causal connection travels at or below the speed of light. For events connected by faster-than-light signals, this protection vanishes. Different observers can disagree not just about the timing, but about the order. Some observers will see the signal being sent before it's received. Others will see it being received before it's sent. And if you combine two faster-than-light signals sent in different directions between observers in relative motion, something truly paradoxical happens. You can receive a reply before you send the original message. This isn't science fiction speculation. It's a well-known thought experiment in physics called the tachyonic antitelephone. It was first described in various forms beginning with Richard Tolman in 1917. The logic is straightforward, and it's the reason most physicists believe faster-than-light communication is truly impossible. Here's how it works. Imagine two people, Alice and Bob. Alice is on Earth. Bob is on a spacecraft moving away from Earth at some significant fraction of the speed of light. Alice has a hypothetical device that can send messages faster than light. She sends a message to Bob at, say, 5 times the speed of light. From Alice's perspective, the message travels from her to Bob. It has a sender and a receiver. It goes from cause to effect, normal. But because the relativity of simultaneity, from Bob's perspective, the situation looks different. Because he's moving relative to Alice, his definition of now is tilted relative to hers. Events that Alice sees as happening at different times, Bob sees as happening at different times in a different way. And for a sufficiently fast signal, Bob actually receives the message before Alice sent it, according to his own perfectly valid reference frame. Now, Bob has his own faster-than-light communicator. He immediately sends a reply back to Alice, also at 5 times the speed of light. From Bob's perspective, he's sending a normal message, but because Alice is moving relative to Bob, the same relativity of simultaneity applies in reverse. Alice receives Bob's reply before she sent her original message. Think about what that means. Alice gets an answer to a question she hasn't asked yet. She receives a response to a message she hasn't written. She could read the reply, decide not to send the original message, and create a logical contradiction, a paradox. The effect, receiving the reply, has preceded the cause, sending the message. Causality has broken down. This isn't a quirk of this particular setup. It's a general feature of any theory that allows faster-than-light signaling in a universe governed by special relativity. The math is unambiguous. If faster-than-light communication is possible, then communication backward in time is also possible. And communication backward in time leads to paradoxes that undermine the logical consistency of the universe. This brings us to the most famous of these paradoxes, the grandfather paradox. You've probably heard of it. You travel back in time and prevent your own grandfather from meeting your grandmother. Your parents are never born, you were never born, but if you were never born, you couldn't have traveled back in time to prevent the meeting. So your grandparents do meet, your parents are born, you are born, and you travel back in time to prevent the meeting. Round and round it goes, a logical loop with no consistent resolution. The grandfather paradox isn't just about grandfathers, of course. It's about any situation where an effect could prevent its own cause. And it's not limited to dramatic scenarios like preventing births. Even the tachyonic anti-telephone creates this kind of paradox. If you receive a reply before you send a message, you could choose not to send the message, but then there's no message for the reply to be replying to. The paradox is inescapable. Now, some physicists have tried to find ways around these paradoxes. There are 2 main approaches, and both reveal something deep about how seriously the universe takes causality. The first approach is the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov. This principle says that time travel might be possible, but only in ways that are self-consistent. You could travel back in time, but you could never do anything that would create a paradox. If you tried to prevent your grandparents from meeting, something would always stop you. You get lost on the way. You'd arrive at the wrong time. You'd change your mind at the last moment. The universe would conspire to prevent any paradox from occurring. In this view, the past is not changeable. Events have already happened, and they happened in a way that includes any time travel that will ever occur. If you traveled back in time, you were always there. Your presence in the past is already part of history. You can't change anything because everything you do has already been done. This is logically consistent, but it raises profound questions about free will. If you travel back in time intending to prevent something, and the universe guarantees you'll fail, do you really have a choice? Are you an agent making decisions, or are you a puppet being guided through a predetermined script? The self-consistency principle preserves causality, but at the cost of freedom. The second approach is far more dramatic. It's the approach advocated by Stephen Hawking, and it's called the chronology protection conjecture. Hawking proposed this in 1992, and it states something bold. The laws of physics do not allow time travel. Period. No exceptions, no loopholes. The universe actively prevents the formation of closed time-like curves. Closed time-like curves are paths through space-time that loop back on themselves, allowing an object or a signal to return to its own past. They're the mathematical structures that would make time travel possible. General relativity, Einstein's theory of gravity, technically allows them. Several exact solutions to Einstein's field equations contain closed time-like curves. Kurt Gödel found one in 1949. A rotating universe in which time travel would be possible, but our universe doesn't appear to rotate in the way Gödel's solution requires. The interior of a rotating Kerr black hole also contains closed time-like curves, but you'd have to cross the event horizon to reach them, which means you'd never be able to report your findings to the outside world. The physicist Frank Tipler showed that an infinitely long, extremely dense rotating cylinder would create closed time-like curves around it. But an infinitely long cylinder is, by definition, physically impossible. And even a very long, very dense cylinder would likely collapse into a black hole before generating any closed time-like curves. Traversable wormholes, if they could be held open with exotic matter, might also be used to create closed time-like curves. Kip Thorne explored this possibility in 1988, showing that if you took one end of a wormhole on a high-speed journey and brought it back, time dilation would mean the two ends of the wormhole connect different times. You could step through one end and emerge from the other end in the past. But Hawking and others showed that as soon as such a time machine is about to form, quantum effects would destabilize it. Vacuum fluctuations, the inherent quantum jittering of empty space, would pile up at the entrance to the time machine, growing without limit. The energy of these fluctuations would become infinite at the moment the closed time-like curve forms, destroying the wormhole and preventing the time machine from ever functioning. This is Hawking's chronology protection conjecture in action. Every time physicists find a theoretical mechanism for building a time machine, something in the laws of physics steps in to prevent it. The exotic matter required doesn't exist. The structures needed are infinitely long. The quantum effects blow up. The wormhole collapses. Every single loophole has a catch. It's as if the universe has a security system designed to prevent time travel, and no matter how clever the break-in attempt, the alarm always goes off. Hawking himself put it memorably. He said the best evidence that time travel is impossible is that we haven't been invaded by tourists from the future. It was a joke, but it carries real weight. If time travel were ever possible at any point in the future, no matter how far into the future, you'd expect time travelers to show up somewhere in the past. The fact that they haven't, as far as we know, suggests that time travel never becomes possible. Some might object that maybe time travelers are hiding, or maybe they can only travel back to the moment their time machine was created, not before. These are valid logical possibilities. But the simpler explanation, the one most consistent with everything we know about physics, is that time travel is simply not allowed. The universe enforces causality. Causes come before effects, always, and the mechanism of enforcement is the speed of light. By preventing anything from traveling faster than light, the universe ensures that events inside each other's light cones always have a consistent ordering. Every observer agrees on which came first. Every observer agrees on the direction of causation. The structure holds. There is something deeply remarkable about this. Causality is not a law of physics in the way that conservation of energy is a law of physics. You won't find an equation called the causality equation. Instead, causality is an emergent property of the structure of space-time itself, combined with the speed of light limit. It arises from the geometry. The light cone structure of space-time, defined by the universal speed limit, automatically separates events into those that can be causally connected and those that cannot. And for those that can be connected, the ordering is absolute. Every observer agrees the cause came first. This means the speed of light is doing something far more important than just limiting how fast spaceships can travel. It's maintaining the logical coherence of the universe. Without it, effects could precede causes, paradoxes would be commonplace, and the basic assumption that the universe is self-consistent would collapse. Think about what self-consistency means for a moment. Every prediction physics has ever made, every equation that describes how the universe works, relies on the assumption that the universe doesn't contradict itself. If you set up an experiment and run it twice under identical conditions, you expect the same result both times. This reproducibility, this consistency, is the foundation of all science. But if causality could be violated, if effects could precede causes, then the universe could contradict itself. An event could both happen and not happen. A particle could be in two contradictory states, not in the quantum mechanical sense where superposition is well defined, but in a genuinely paradoxical sense where the laws of logic break down. The universe seems to regard this as unacceptable, and it enforces its consistency through the speed of light. Let me give you an analogy to make this feel more concrete. Imagine a vast spreadsheet, a cosmic ledger where every event in the universe is recorded. Each event has a time, a location, and a description of what happened. The speed of light ensures that this ledger can never contain a contradiction. If event A causes event B, then A always appears earlier in the ledger than B for every observer, in every reference frame, without exception. Now imagine what would happen if you could write entries in this ledger out of order. If you could make an effect appear before its cause, the ledger would become inconsistent. It would contain contradictions, and a contradictory ledger is useless. It doesn't describe anything. It's not a record of reality. It's nonsense. The speed of light prevents this. It ensures that the cosmic ledger remains consistent, that causes always precede effects, that the universe always makes sense, even if that means forbidding faster than light travel, even if that means trapping us within our light cones, even if that means the stars will forever be separated by years and decades and centuries of travel time. This has implications that go far beyond space travel. It means there are events happening right now, at this very moment, all across the universe, that you can never influence and that can never influence you. Stars are exploding, planets are forming, civilizations might be rising and falling, and none of it has anything to do with you, because none of it is inside your light cone. You are trapped in your own bubble of causality, connected only to events that light has had time to link to your location. This has a haunting implication for the question of whether we are alone in the universe. Even if intelligent civilizations are common, even if millions of them exist right now, scattered across the galaxy and beyond, they may never know about each other. Their light cones may never meaningfully overlap. A civilization that arose 10,000 years ago on a planet 50,000 light years away hasn't received our earliest radio signals yet. We haven't received theirs. And if either civilization lasts only 100,000 years, a generous estimate by historical standards, the signals might arrive long after the sender has gone extinct. The silence of the cosmos, the strange absence of signals that physicists call the Fermi paradox, might not be evidence that we're alone. It might be evidence that causality is a cage, that the universe is full of prisoners who can never reach each other's cells. The universe is not a single stage where everything happens simultaneously and everyone can interact with everyone else. It's a vast collection of overlapping light cones, each one defining a different set of causal connections. Your light cone is different from someone on Mars, which is different from someone on a planet orbiting Proxima Centauri, which is different from someone in the Andromeda galaxy. Each observer has their own bubble of causality, their own set of events they can influence and be influenced by. And these bubbles are finite, limited by the speed of light and the age of the universe. We live in a universe where causality is local. What happens here can only affect what's nearby, and only after enough time has passed for the influence to travel at or below the speed of light. This locality, this insistence that causes and effects must be connected by a chain of events that never exceeds the speed of light, is one of the deepest principles in all of physics. It's called the principle of locality, and it underlies virtually every successful physical theory we have. But the universe's insistence on protecting causality raises a profound question. Is the universe protecting causality because it must, or because it can? Is causality a fundamental feature of reality that cannot be violated under any circumstances? Or is it a feature that happens to be preserved by the particular laws of physics we've discovered so far, but could in principle be violated by some deeper theory we haven't found yet? Most physicists lean toward the first answer. Causality appears to be non-negotiable. Every attempt to construct a self-consistent physical theory that violates causality has failed. Every experimental test has confirmed that causes precede effects. Every theoretical loophole has turned out to have a catch. The universe doesn't just happen to preserve causality, it seems to demand it. And the price of that demand is the speed of light, the wall that cannot be crossed, the limit that cannot be exceeded, the boundary that keeps the universe logically coherent, even if it means we can never reach the stars in a single lifetime. His speed of light limits how fast anything can move or any signal can travel. And causality, enforced by that speed limit, ensures that the universe remains logically consistent, that causes always precede effects, and that paradoxes are forbidden. But the universe's restrictions don't end at the large scale. They go all the way down to the smallest possible scales, to the quantum world where reality itself becomes fuzzy, uncertain, and fundamentally unknowable. Because it turns out the universe doesn't just limit what you can do, it limits what you can know. And that boundary, the blur at the very bottom of reality, may be the most unsettling of all. The speed of light limits what you can do. Causality limits what you can influence. These are boundaries on action, on movement, on reach. But the universe has another kind of boundary. You can't travel faster than light. You can't break the chain of cause and effect. These are boundaries on action, on movement, on influence. But the universe has another kind of boundary, one that's arguably even more unsettling. A limit not on what you can do, but on what you can know. Because it turns out that at the smallest scales, reality itself becomes blurry. Not blurry in the way that a photograph is blurry, where the details exist, but you just can't see them clearly. Blurry in a much deeper sense. The details don't exist. They aren't there. They aren't hiding behind some curtain waiting to be revealed by a better instrument. They genuinely, fundamentally do not exist until something forces them to. This is the world of quantum mechanics. And it contains boundaries just as absolute and just as unbreakable as the speed of light. Let's start with something you do every day without thinking about it. You look at a ball sitting on a table. You can see where it is. You can measure its position with a ruler. You can also watch it move and measure how fast it's going. You can know both things at the same time. Its position and its velocity, as precisely as you want. If your ruler isn't precise enough, you get a better ruler. If your stopwatch isn't accurate enough, you get a better stopwatch. In everyday life, the precision of your knowledge is limited only by the quality of your instruments. There's no fundamental barrier. The ball has a definite position and a definite velocity, and with good enough tools, you can know both to whatever degree of accuracy you desire. This seems so obviously true that questioning it feels absurd. Of course, objects have definite positions and velocities. Of course, you can measure both. What else could possibly be the case? But in 1927, a German physicist named Werner Heisenberg discovered something that shattered this assumption completely. He found that at the quantum scale, at the level of atoms and subatomic particles, you cannot know both the position and the momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you can know the other. And this is not because your instruments aren't good enough. It's because the particle does not have a precise position and momentum simultaneously. The information simply does not exist. This is the Heisenberg uncertainty principle. And it is one of the most important and most misunderstood ideas in all of science. The uncertainty principle is expressed mathematically as a simple inequality. The uncertainty in a particle's position, which physicists call delta x, multiplied by the uncertainty in its momentum, delta p, must always be greater than or equal to a specific tiny number. That number is Planck's constant divided by 4 pi, often written as h bar over 2. Planck's constant is incredibly small, about 6.626 times 10 to the minus 34 joule seconds. This is why we don't notice quantum uncertainty in everyday life. For objects as large as a ball or even a grain of dust, the uncertainty is so small that it's completely undetectable. The ball on the table does have a position and momentum that are defined precisely enough for any practical purpose. But for an electron, a proton, or any subatomic particle, the story is completely different. These particles are so small and so light that the uncertainty becomes significant. If you try to pin down an electron's position to within the width of an atom, roughly 1/10 billionth of a meter, its momentum becomes wildly uncertain. You might find the electron here, or you might find it moving at a completely different speed in a completely different direction. The more tightly you try to confine it, the more violently it resists being pinned down. And if you try the other approach, measuring the electron's momentum very precisely, its position becomes correspondingly uncertain. An electron with a very precisely known momentum could be essentially anywhere. Not just anywhere in the room, anywhere in the universe in principle. The more precisely you know how fast it's going, the less you know about where it is. Now, I need to address something crucial because this is where most explanations go wrong. The uncertainty principle is not about measurement disturbing the particle. This is the most common misconception, and it's deeply misleading. You've probably heard explanations like this. To measure a particle's position, you have to bounce a photon off it. The photon hits the particle and changes its momentum. So the act of measuring the position disturbs the momentum, and that's why you can't know both. This is called the observer effect, and while it's a real phenomenon, it is not the uncertainty principle. They are completely different things. The observer effect is about measurement being clumsy. It's about the practical difficulty of looking at something without poking it. In principle, you could imagine a gentler measurement, one that disturbs the particle less. You could imagine improving your technique, developing better instruments, finding cleverer ways to measure without interfering. The uncertainty principle says none of that matters. Even with a perfect measurement device, one that doesn't touch the particle at all, one that magically extracts information without any physical interaction whatsoever, you still cannot know both position and momentum precisely. Because the particle does not have a precise position and momentum simultaneously. It's not that the information is hidden from you. It's not that the particle knows where it is but refuses to tell you. The particle genuinely, objectively, does not possess definite values for both properties at the same time. This is almost impossible to accept because it violates everything our intuition tells us about how objects work. We're used to a world where things have definite properties whether we look at them or not. The moon is there whether anyone observes it or not. Your car is parked where you left it, even when you're not looking at it. But at the quantum level, this assumption breaks down. Quantum particles exist in a state of superposition, a combination of many possible positions and momenta all at once, until a measurement forces them to adopt a specific value. The measurement doesn't reveal a property that was already there. It creates the property. Before the measurement, the property didn't exist. Albert Einstein hated this idea. He famously asked whether the moon exists only when someone looks at it. He spent the last decades of his life trying to prove that quantum mechanics was incomplete, that particles really do have definite properties, and we just haven't figured out how to see them. He proposed hidden variable theories, arguing that there must be some deeper level of reality where everything is precise and determined, and quantum uncertainty is just an illusion created by our ignorance of these hidden variables. But Einstein was wrong. In 1964, physicist John Bell devised a mathematical test that could distinguish between quantum mechanics and any hidden variable theory. The test involved measuring correlations between pairs of entangled particles. If hidden variables existed, the correlations would obey a certain inequality, now called Bell's inequality. If quantum mechanics was right and the particles genuinely lacked definite properties until measured, the correlations would violate that inequality. The experiments have been done many times, with increasing precision and with every possible loophole being closed, one by one, over decades. Most recently in 2015, when a team in the Netherlands performed a loophole-free Bell test that closed the last remaining experimental gaps. The result is unambiguous. Bell's inequality is violated. Hidden variables of the type Einstein envisioned do not exist. Quantum uncertainty is not a result of ignorance. It is a fundamental feature of reality. The universe is genuinely, irreducibly fuzzy at the quantum level. The Bell test experiments revealed something else, something that Einstein found even more disturbing than uncertainty itself. Quantum entanglement. When two particles interact and become entangled, their quantum states become linked. Not linked in the way that two coins might be linked if you put one in each pocket and walked away. In that case, each coin already has a definite state, heads or tails, and looking at one simply tells you about the other. Entanglement is fundamentally different. Neither particle has a definite state until one of them is measured, but the moment you measure one, the other instantly adopts a correlated state, no matter how far apart they are. Measure the spin of one electron and find it pointing up, and its entangled partner, whether it's across the room or across the galaxy, will be found pointing down, instantly, not at the speed of light. Instantly. Einstein called this spooky action at a distance, and he refused to believe it was real. He argued it proved quantum mechanics must be incomplete, that there must be hidden variables predetermining the outcomes. But Bell's theorem and the experiments that followed proved Einstein wrong. The correlations are real. The outcomes are not predetermined, and yet no information travels between the particles. This last point is crucial. You cannot use entanglement to send a message faster than light. The results of measurements on entangled particles appear random to each observer individually. The correlations only become visible when the observers compare their results, and that comparison requires a conventional signal, limited by the speed of light. The universe permits this strange, instantaneous connection while still protecting causality. Spooky, yes, but not a loophole. The uncertainty principle applies not just to position and momentum, it applies to many pairs of physical properties. Energy and time have their own uncertainty relation. You cannot measure the energy of a quantum system with arbitrary precision in an arbitrarily short time. The more precisely you want to know the energy, the longer you have to wait. The shorter your measurement window, the less precise your energy measurement becomes. This has extraordinary consequences. One of them is the existence of virtual particles. The energy-time uncertainty principle means that in very short time intervals, the energy of a system can fluctuate by significant amounts. In intervals short enough, these fluctuations are large enough to produce particle-antiparticle pairs that pop into existence briefly before annihilating each other and disappearing. These are called virtual particles, and they fill the vacuum of space. What we think of as empty space is actually a seething foam of particles appearing and vanishing constantly, borrowing energy from the vacuum for the briefest of instants. This isn't speculation. Virtual particles have measurable effects. The Casimir effect, first predicted in 1948 and experimentally confirmed in 1997, demonstrates that two uncharged metal plates placed very close together in a vacuum will experience a small but measurable force pulling them together. This force exists because the virtual particles between the plates are restricted by the plate's presence. Fewer virtual particles can exist between the plates than outside them. The imbalance creates a net inward pressure. The Casimir effect has been measured with high precision, and the results match quantum mechanical predictions beautifully. Virtual particles are real, the vacuum is not empty, and all of this is a consequence of the uncertainty principle. Quantum tunneling is another consequence. Sometimes a particle can pass through a barrier that, according to classical physics, it doesn't have enough energy to cross. An electron encountering a wall of higher energy should bounce off, just as a ball thrown against a wall bounces back. But quantum particles don't always play by these rules. Because the particle's position is uncertain, there's a probability that it's on the other side of the barrier, even though it doesn't have enough energy to climb over it. And sometimes, that probability becomes reality. The particle appears on the other side as if it tunneled straight through. This isn't a theoretical curiosity. Quantum tunneling is why the sun shines. The protons in the sun's core don't actually have enough energy to overcome their mutual electromagnetic repulsion and fuse together. The temperatures and pressures are close, but not quite high enough. Classical physics says fusion shouldn't happen. But quantum tunneling allows the protons to occasionally bypass the energy barrier and fuse, releasing enormous amounts of energy. Without quantum tunneling, nuclear fusion in the sun would be virtually impossible, and the sun would not shine, stars would not exist, and neither would we. Now let's go even deeper. Let's talk about the absolute flaw of physical reality, the Planck scale. In 1899, the German physicist Max Planck identified a set of natural units derived from fundamental physical constants. By combining the speed of light, Newton's gravitational constant, and the reduced Planck constant, you can construct units of length, time, and mass that don't depend on any human conventions. These are the Planck units, and they represent the scales at which quantum effects and gravitational effects become equally important. The Planck length is approximately 1.6 times 10 to the minus 35 meters. That is unimaginably small. To put it in perspective, if you expanded an atom to the size of the entire observable universe, a Planck length would be roughly the size of a medium tree. The Planck length is as many orders of magnitude smaller than an atom as an atom is smaller than the observable universe. It occupies a scale so far below our everyday experience that calling it small doesn't remotely capture it. The Planck time is the time it takes light to travel one Planck length. That's approximately 5.4 times 10 to the minus 44 seconds. In the time it takes you to blink your eye, roughly 1/3 of a second, about 6 times 10 to the 43 Planck times have elapsed. That's a number with 43 digits. What happens at the Planck scale? Honestly, we don't know. Our two best theories of physics, quantum mechanics and general relativity, both work extraordinarily well in their respective domains. Quantum mechanics describes the behavior of the very small with astonishing accuracy. General relativity describes the behavior of gravity and the very large with equally astonishing accuracy. But when you try to apply both theories simultaneously at scales where both quantum effects and gravitational effects are significant, the mathematics breaks down. The equations produce infinities and nonsensical results. This breakdown happens at the Planck scale, below the Planck length and before the Planck time. Our understanding of physics simply stops working. The very concepts of space and time may lose their meaning. Space might become foamy, granular, or something entirely unlike the smooth continuum we experience. Time might not flow in the way we understand it. The geometry of space-time itself might become subject to quantum uncertainty, fluctuating wildly and unpredictably. We don't have a theory that works at this scale. This is the domain where a theory of quantum gravity, a theory that successfully unifies quantum mechanics and general relativity, would be needed. String theory is one candidate, loop quantum gravity is another. But neither has been experimentally confirmed, and both remain works in progress. The Planck scale represents a boundary of human knowledge, a floor below which our physics cannot see. There's another quantum boundary that's just as absolute, even if it's less well known. It's called the no-cloning theorem, and it was proven in 1982 by physicists William Wouters, Wojciech Zurek, and independently by Dennis Deeks. The no-cloning theorem states that it is impossible to create an identical copy of an arbitrary unknown quantum state. You cannot take a particle in some unknown quantum state and produce a second particle in exactly the same state while leaving the original intact. This is not an engineering limitation. It's a mathematical proof derived directly from the fundamental laws of quantum mechanics. No technology, no matter how advanced, can violate it. This might sound like a minor technical detail, but its implications are enormous. The no-cloning theorem means that quantum information is fundamentally different from classical information. Classical information can be copied freely. You can photocopy a document. You can duplicate a computer file. You can write down a number and give copies to 100 people. But quantum information cannot be copied. Each quantum state is unique and irreproducible. This has practical consequences for quantum computing. A quantum computer can process information in ways a classical computer cannot, exploiting superposition and entanglement to perform certain calculations vastly faster. But the no-cloning theorem means quantum error correction is fundamentally harder than classical error correction. You can't just make backup copies of quantum data the way you backup files on a hard drive. Researchers have found ingenious workarounds, but the underlying limitation remains. The universe forbids perfect copying of quantum information. The no-cloning theorem also connects to the fundamental limits on knowledge. If you can't copy a quantum state, you can't fully characterize it with a single measurement. You can measure one property, but the measurement generally disturbs the state, destroying information about other properties. To fully characterize a quantum state, you'd need many identical copies to measure, taking different measurements on each copy. But the no-cloning theorem says you can't make those copies if you start with a single unknown particle. The information trapped in a single quantum particle is, in a very real sense, partially inaccessible. Let's talk about the measurement problem, because it sits right at the heart of quantum mechanics and represents perhaps the deepest unresolved puzzle in all of physics. When a quantum system is not being measured, it evolves according to the Schrödinger equation. a smooth, deterministic mathematical law. A particle in superposition, existing in multiple states simultaneously, evolves predictably. If you know the quantum state at one time, you can calculate what it will be at any future time. In this sense, quantum mechanics is perfectly deterministic. But when you make a measurement, something changes. The superposition appears to collapse. The particle, which was in a combination of many possible states, suddenly adopts one specific state. And which state it adopts is random. Not random in the way that a coin flip is random, where the outcome is in principle determined by the initial conditions but too complex to predict in practice. Random in a deeper sense. There is no hidden mechanism determining the outcome. The universe itself hasn't decided until the moment of measurement. This is deeply troubling to physicists. The Schrödinger equation is smooth and continuous. Measurement is sudden and discontinuous. The Schrödinger equation is deterministic. Measurement is random. These two descriptions seem fundamentally incompatible, and yet both are essential parts of quantum mechanics. The smooth evolution describes what happens between measurements. The sudden collapse describes what happens during measurements. But nowhere in the theory is there a clear boundary between these two regimes. What counts as a measurement? How big does the system have to be before quantum superposition gives way to definite classical outcomes? We don't know. There are several interpretations of quantum mechanics that attempt to resolve this puzzle. And the remarkable thing is that they all make the same experimental predictions. We literally cannot distinguish between them using any currently known experiment. The Copenhagen interpretation, the oldest and most widely taught, essentially says that the collapse is real and fundamental. When you measure a quantum system, the wave function really does collapse. But it doesn't explain why or how. The many worlds interpretation says the wave function never collapses. Instead, every possible outcome of every measurement actually occurs, each in its own branching universe. When you measure an electron's spin and get up, there's another branch of the universe where you got down. Both outcomes are real. Both U's continue existing, forever unaware of each other. This avoids the collapse problem, but at the cost of an incomprehensibly vast number of parallel universes. Decoherence theory explains how quantum superpositions become effectively classical through interaction with the environment. When a quantum system interacts with a large number of environmental particles, the interference effects that make quantum mechanics strange become spread out and undetectable. The system appears to collapse into a definite state, even though technically it's still in a superposition with its environment. This explains why large objects behave classically, but it doesn't fully resolve the measurement problem because it doesn't explain why we perceive one specific outcome, rather than the full superposition. The measurement problem is not just a philosophical curiosity. It represents a genuine gap in our understanding of how the universe works. We have a theory that makes incredibly precise predictions about the outcomes of experiments, but we don't fully understand what the theory is saying about reality. The universe operates according to rules we can use, but haven't fully deciphered. No discussion of quantum mechanics would be complete without the most famous thought experiment in physics. In 1935, Austrian physicist Erwin Schrödinger proposed a scenario designed to show just how strange quantum mechanics really is. Imagine a cat sealed inside a box with a tiny amount of radioactive material, a Geiger counter, and a vial of poison. If a single atom decays, the Geiger counter triggers, the vial breaks, and the cat dies. If no atom decays, the cat lives. Radioactive decay is a quantum process. Before measurement, the atom is in a superposition of decayed and not decayed. According to quantum mechanics, until someone opens the box and checks, the atom hasn't decided. It's in both states at once. And if the atom is in both states, then the Geiger counter is in both states, and the vial is in both states, and the cat is in both states. Alive and dead, simultaneously. Schrödinger didn't propose this because he believed cats could be simultaneously alive and dead. He proposed it as a critique. He was trying to demonstrate that something had gone terribly wrong with quantum theory, that its implications were so absurd they couldn't possibly be right. But here's the uncomfortable truth. Every experiment we've ever conducted is consistent with quantum mechanics. The theory hasn't been wrong yet. Schrödinger's cat was meant to expose a flaw in quantum mechanics. Instead, it exposed a flaw in human intuition. The universe is under no obligation to make sense to us at the scale of cats and boxes. It follows its own rules, and those rules permit superposition whether we find it reasonable or not. What does all of this mean for the dream of perfect knowledge? For the idea that with enough technology, enough intelligence, enough patience, we could in principle know everything about the physical world? It means that dream is dead. The universe has a built-in resolution limit. Below a certain scale, reality is not just unknown, but genuinely unknowable. A particle doesn't have a precise position and momentum at the same time. The vacuum isn't empty, but seethes with fluctuations that obey no one's commands. Quantum states cannot be copied or fully characterized from a single specimen. Measurement outcomes are fundamentally random, not merely unpredictable. Even with a computer the size of the observable universe, even with instruments of unlimited precision, even with infinite time and patience, there are things about the quantum world that you simply cannot know. Not because you aren't clever enough, not because your technology is too primitive, but because the answers don't exist until the moment you create them by looking. The universe keeps secrets not by hiding them, but by not having them. This is a fundamentally different kind of boundary from the speed of light or the protection of causality. Those boundaries tell you what you cannot do. The uncertainty principle tells you what you cannot know. It's a limit on information itself, on the resolution of reality, on the sharpness of existence at the smallest scales. Below a certain point, the universe is blurry, irreducibly, permanently, fundamentally blurry. And this blur is not a flaw. It's a feature. Without quantum uncertainty, atoms couldn't exist. The electrons in atoms don't orbit the nucleus like planets orbit a star. They exist in probability clouds, smeared out over a region of space, their exact position undefined. This smearing is what gives atoms their size and structure. Without it, electrons would spiral into the nucleus. Atoms would collapse. Matter would not exist. And neither would you. Without quantum tunneling, stars wouldn't shine. Without virtual particles, the forces that hold atoms together wouldn't work the way they do. Without the energy-time uncertainty relation, The early universe couldn't have produced the density fluctuations that eventually grew into galaxies and stars and planets. The blur at the bottom of reality is not just a limitation, it's the foundation on which everything else is built. So the universe has drawn three boundaries around us. The speed of light limits how fast we can move and how far our influence can reach. Causality ensures that cause always precedes effect, maintaining the logical consistency of the universe at the cost of forbidding faster than light travel and time travel. And quantum uncertainty limits what we can know about the fundamental building blocks of reality, ensuring that below a certain scale, the universe remains forever fuzzy and unpredictable. But there's one more set of boundaries to explore, and these might be the most haunting of all. Because when you look outward, away from the quantum world and toward the largest scales of the cosmos, the universe draws boundaries around what you can see, what you can reach, and ultimately, what can survive. There are horizons out there, edges beyond which light cannot pass, information cannot flow, and even the universe itself is slowly, inexorably winding down. These final walls are not made of energy or geometry or quantum law. They're made of time, and they're closing in on everything that exists. Look up at the night sky on a clear evening, far from city lights, and you'll see thousands of stars scattered across the darkness. Behind them, if your eyes are sharp and the conditions are right, you'll see the faint glow of the Milky Way stretching overhead. It feels like you're looking at everything, like the entire universe is laid out before you, visible if only you had strong enough eyes or a powerful enough telescope. But you're not seeing everything. You're not even close. You're seeing a tiny fraction of what exists, and no amount of technology will ever change that. Because the universe has edges. Not edges in the way that a table has edges, where you can walk around and see the other side. These are edges of a fundamentally different kind. They're horizons. Boundaries beyond which no light can reach you, no signal can arrive, no information of any kind can ever pass. And they're not out there in the distance, waiting to be reached. They're woven into the structure of space-time itself, as permanent and as unbreakable as the speed of light that creates them. The most straightforward of these horizons is the boundary of the observable universe. The universe is approximately 13.8 billion years old. Light travels at a finite speed. So there's a maximum distance from which light could have reached us since the universe began. Any light that started its journey toward us more than 13.8 billion years ago has had that long to travel. Light from anything farther away simply hasn't arrived yet. It's still on its way, crossing the void between us at 300,000 kilometers per second. But it hasn't made it here. Now, you might think this means the observable universe is 13.8 billion light years in radius. But it's actually much larger than that, about 46.5 billion light years in every direction. This is because space itself has been expanding during all those billions of years that the light has been traveling. When a photon left a distant galaxy 13 billion years ago, that galaxy was much closer to us than it is now. While the photon was crossing the intervening space, the space itself was stretching, carrying that galaxy farther and farther away. By the time the photon arrives at our telescopes, the galaxy that emitted it has been carried by the expansion of space to a distance far greater than 13 billion light years. The observable universe is therefore about 93 billion light years across. That's the diameter of the sphere from which light has had time to reach us, accounting for the expansion of space during the light's journey. Within this sphere, astronomers estimate there are roughly 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. And most of those stars probably have planets. The observable universe is staggeringly, incomprehensibly vast. But here's what makes this a true boundary. Everything beyond the observable universe is invisible to us. Not because our telescopes aren't powerful enough, not because the light is too faint, but because the light hasn't had time to reach us. No telescope, no matter how large, no matter how sensitive, no matter what wavelength of light it detects, can see beyond this horizon. The information simply isn't here yet. It's a fundamental limit imposed by the finite speed of light and the finite age of the universe. And it gets worse, much worse, because the universe's expansion isn't just continuing, it's accelerating. In 1998, 2 independent teams of astronomers made one of the most shocking discoveries in the history of science. By studying distant supernovae, they found that the expansion of the universe is speeding up. Galaxies aren't just moving apart, they're moving apart faster and faster over time. Something is pushing the universe apart, counteracting gravity and driving space to expand at an ever-increasing rate. This something is called dark energy, and despite being the dominant component of the universe, making up about 68% of its total energy content, we have almost no idea what it is. Dark energy creates a second horizon, one that's even more disturbing than the boundary of the observable universe. This is the cosmic event horizon. Because the expansion of space is accelerating, there are galaxies that we can currently see whose light will never reach us again. They're being carried away by the expansion of space faster than their light can cross the growing gap between us. Right now, we can observe their ancient light. Photons that left those galaxies billions of years ago when they were closer, and the expansion was slower. But any light those galaxies emit today will never arrive here. They've already crossed our cosmic event horizon. They're gone, and they're not coming back. The expansion of space is not something that can be reversed by any known force. It's not like a current you can swim against. Space itself is growing between us and those distant galaxies, and the more space there is, the faster it grows, because dark energy fills every cubic meter of space with a constant energy density. More space means more dark energy means faster expansion means more space. It's a runaway process. The numbers are staggering. Approximately 94% of the galaxies currently within the observable universe are already beyond our cosmic event horizon. We can see their light from the past, but we could never send them a message that would arrive. They are causally disconnected from our future. We can observe their history, but we can never participate in their present or their future. They're like photographs of people who have already walked away forever. You can look at the picture, but you can't call them back. And every day, more galaxies slip beyond the horizon. The expansion carries them past the point of no return. In the far future, billions of years from now, the night sky will be much emptier. Almost all the galaxies we can see today will have been carried beyond the cosmic event horizon. Any intelligent beings living in our galaxy at that distant time will look out at the sky and see nothing but the stars of their own galaxy and its nearest neighbors, which will have merged together by then. They'll have no evidence that the universe contains anything else. The cosmic microwave background, the afterglow of the Big Bang, will have been stretched by expansion to wavelengths so long that it becomes undetectable. The evidence for the Big Bang itself will have been erased by the expansion of space. Those future astronomers will live in a universe that appears to contain only their own galaxy, floating in an infinite void. They'll have no way to know what we know. The evidence will be gone, carried beyond the horizon forever. This is a boundary not just in space, but in knowledge. The expansion of the universe is actively destroying information, carrying evidence of the cosmos beyond the reach of any possible observer. The universe is pulling itself apart, hiding its own history behind an ever-expanding curtain of accelerating space. Now let's talk about a different kind of horizon. One that's more dramatic, more violent, and in some ways even more absolute. The event horizon of a black hole. A black hole forms when a massive star dies and its core collapses under its own gravity. If the core is massive enough, no known force can halt the collapse. The matter falls inward, compressing to unimaginable density, and gravity becomes so strong that not even light can escape. The boundary around this region of inescapable gravity is called the event horizon. The event horizon is not a physical surface. You can't touch it or stand on it. It's a mathematical boundary, a point of no return defined by geometry. Once you cross the event horizon, every possible path through space-time, no matter which direction you try to move, leads deeper into the black hole, toward the singularity at the center. It's not that you can't move fast enough to escape. It's that the geometry of space-time inside the event horizon curves so completely inward that outward simply doesn't exist anymore. Every direction is inward. Every path leads to the singularity. You are as trapped as a person falling off a cliff is trapped by gravity, except infinitely more so, because there is no ground to land on, only the singularity, where the curvature of space-time becomes infinite, and our physics breaks down entirely. From outside the black hole, the event horizon appears as a dark sphere. Light from objects behind the black hole bends around it, creating a characteristic warping effect. Stars and galaxies behind the black hole appear distorted, their light curved by the intense gravity. The Event Horizon Telescope collaboration captured this effect directly in 2019 when they produced the first image of a black hole shadow, the supermassive black hole at the center of the galaxy M87. That image, a glowing ring of light surrounding a dark central shadow, shows the boundary between the universe we can interact with and a region from which no information can ever return. If you watch someone fall into a black hole from a safe distance, you'd see something strange. As they approach the event horizon, the light from their body would be increasingly redshifted, stretched to longer and longer wavelengths by the intense gravity. They would appear to slow down, their movements becoming sluggish. Their image would grow dimmer and redder, and right at the event horizon, they would appear to freeze completely. Their image fading to invisibility as the light they emit is stretched to infinite wavelength. From your perspective, they never quite cross the horizon. They asymptotically approach it, growing ever dimmer, but never quite disappearing. But from the falling person's perspective, nothing special happens at the event horizon. They cross it without fanfare. There's no wall, no barrier, no sign that sees point of no return. The event horizon is locally indistinguishable from ordinary space. It's only globally, when you try to escape, that you discover you can't. You've crossed a boundary that you can't uncross. And once inside, you have a limited amount of time before you reach the singularity. For a stellar mass black hole, this time might be only microseconds. For a supermassive black hole like the one at the center of the Milky Way, which has a mass of about 4 million times the mass of the Sun, you might have several hours. But regardless of how long you have, the outcome is certain. You will reach the singularity. No force in the universe can prevent it. The singularity is not a place in space that you can avoid by steering in a different direction. Inside the event horizon, the singularity is in your future. It's a moment in time, not a point in space. And just as you cannot avoid tomorrow, you cannot avoid the singularity once you're inside the horizon. Black holes raise one of the deepest unsolved problems in physics. It's called the black hole information paradox, and it strikes at the very foundations of our understanding of the universe. Quantum mechanics has a fundamental rule: information is never destroyed. The complete quantum state of a system at any moment contains all the information needed to reconstruct the state at any other moment, past or future. This is called unitarity, and is one of the cornerstones of quantum theory. If you burn a book, the information in the book isn't truly destroyed. In principle, if you could track every particle of ash, every photon of light, every molecule of gas produced by the fire, you could reconstruct the book's contents. The information is scrambled, spread out, practically impossible to recover, but it's still there. Quantum mechanics guarantees it. But when matter falls into a black hole, the information it carries seems to vanish behind the event horizon, inaccessible to the outside universe. And Stephen Hawking showed in 1974 that black holes aren't truly permanent. They slowly evaporate through a process now called Hawking radiation. Due to quantum effects near the event horizon, particle-antiparticle pairs are constantly being created. Normally these pairs annihilate each other almost instantly, but near the event horizon, one particle can fall in while the other escapes. The escaping particle carries energy away from the black hole, causing it to slowly shrink. Over incomprehensibly long time spans, the black hole evaporates completely, leaving nothing behind. Here's the problem. Hawking radiation appears to be perfectly thermal, meaning it carries no information about what fell into the black hole. It's like the heat radiating from a stove. The heat tells you the stove is hot, but it doesn't tell you what's cooking. If a book falls into a black hole and the black hole eventually evaporates into featureless thermal radiation, the information in the book is truly destroyed. Gone. Not scrambled, not hidden, not rearranged. Actually destroyed. But quantum mechanics says information cannot be destroyed. General relativity says the event horizon hides the information. Hawking radiation says the black hole will eventually disappear. These three facts are mutually contradictory. At least one of them must be wrong or incomplete, and we don't know which one. This paradox has consumed theoretical physics for 5 decades. Various resolutions have been proposed. Perhaps the information is somehow encoded in the Hawking radiation in a way we don't yet understand. Perhaps it's stored on the event horizon itself, like data on a hard drive. Perhaps the information escapes through some unknown mechanism when the black hole reaches its final stages of evaporation. Perhaps our understanding of space-time needs to be revised at the most fundamental level. The black hole information paradox represents a boundary of our understanding. It's a place where our two best theories of physics, quantum mechanics, and general relativity give contradictory answers. Resolving it will likely require a theory of quantum gravity, and that theory doesn't exist yet. The paradox is a wall we cannot currently see past. Now let's turn to the most absolute boundary of all, the one that limits not just what we can do or what we can know, but what can exist. The second law of thermodynamics. The second law states that in any closed system, entropy, which is a measure of disorder, or more precisely the number of possible microscopic arrangements consistent with a system's macroscopic properties, always increases or stays the same. It never decreases. Things fall apart. Order dissolves into disorder. Hot objects cool down. Cold objects warm up. Concentrated energy spreads out. Structure erodes. Complexity decays. This isn't just an observation about everyday objects. It's one of the most fundamental and inviolable laws in all of physics. Arthur Eddington, the physicist who confirmed Einstein's general relativity through solar eclipse observations, once said that if your theory contradicts the second law of thermodynamics, there is no hope for it. The second law occupies a special place in physics, even more fundamental, some would argue, than conservation of energy or the speed of light. And the universe is a closed system. There is no outside from which new energy or order can be imported. The total entropy of the universe is increasing, has been increasing since the Big Bang, and will continue increasing until it reaches its maximum value. When that happens, the universe will have reached a state called thermodynamic equilibrium, a state of maximum entropy where no gradients exist. No differences in temperature or density or energy can be found anywhere, and therefore no work can be done, no processes can occur, no structures can form, and no life can exist. This is called the heat death of the universe, and it is the final boundary, the ultimate wall that physics cannot cross. The timeline of the heat death stretches almost beyond comprehension. In the relatively near future, cosmically speaking, star formation will gradually wind down. The raw materials, clouds of hydrogen and helium gas, are being consumed. In about 100 trillion years, the last stars will burn out. Red dwarfs, the smallest and longest-lived stars, will exhaust their hydrogen fuel and fade away. The universe will go dark. No more starlight. No more stellar energy to power planetary surfaces or warm any remaining life. After the stars die, the universe enters what physicists call the degenerate era. The only objects remaining will be stellar corpses, white dwarfs slowly cooling toward absolute zero, neutron stars spinning down and dimming, black holes sitting silently in the darkness, and vast clouds of cold gas and dust, too diffuse to ever collapse into new stars. Over even longer timescales, matter itself may decay. Protons, which are currently believed to be stable, might eventually decay into lighter particles. Various theories of particle physics predict that protons have a finite lifetime, perhaps around 10 to the power of 40 years. If proton decay occurs, then over these incomprehensible timescales, all matter, every atom, every particle that makes up every structure in the universe will gradually dissolve. Solid objects, planets, white dwarfs, even neutron stars will slowly evaporate as their constituent protons decay one by one. Black holes will be the last macroscopic objects to survive, but even they aren't permanent. Hawking radiation ensures that every black hole, given enough time, will evaporate completely. A stellar mass black hole will take roughly 10 to the power of 67 years to evaporate. A supermassive black hole, like the one at the center of the Milky Way, will take about 10 to the power of 100 years. That's a 1 followed by 100 zeros, a number so large that writing it out in full would take more digits than there are atoms in the observable universe. But eventually even the last black hole will evaporate, and then there will be nothing left but a diffuse gas of photons, neutrinos, and perhaps electrons and positrons, all at incredibly low energies, spread across a universe so vast and so empty that no two particles will ever interact again. The temperature of the universe will approach absolute zero, though never quite reaching it. The entropy will be at its maximum. Nothing will ever happen again. No structures will form, no processes will occur, no energy will flow from hot to cold, because there will be no hot and no cold. Just a uniform, featureless void stretching forever in all directions and forever into the future. Or will nothing happen? Some physicists have raised a deeply unsettling possibility. In a universe at maximum entropy, random quantum fluctuations still occur. Given enough time and in an eternal void there is nothing but time, these fluctuations could, purely by chance, assemble a momentary configuration of matter complex enough to constitute a conscious mind, complete with false memories of a life it never lived, a universe it never inhabited, a history that never happened. These hypothetical entities are called Boltzmann brains, named after the 19th century physicist Ludwig Boltzmann. And here's what makes them so disturbing. Over truly infinite timescales, the random assembly of a single brain with false memories is overwhelmingly more probable than the random assembly of an entire universe with real ones. If the universe lasts forever, it will produce unimaginably more Boltzmann brains than it will ever produce real observers. Some cosmologists find this so troubling that they consider it a genuine constraint on theories of the far future. A viable cosmological theory, they argue, shouldn't predict that almost all observers are hallucinating brains floating in the void. The fact that this concern is taken seriously by working physicists tells you something about how strange the ultimate fate of the universe really is. This is the ultimate boundary. Not a wall in space, but a wall in time. The universe has a direction, and that direction is toward maximum entropy, toward disorder, toward the dissolution of every structure and every gradient that makes anything possible. Every star, every galaxy, every living thing is a temporary island of order in a rising sea of entropy. We exist because the universe started in an extraordinarily low entropy state at the Big Bang. and entropy has been increasing ever since. The flow from low entropy to high entropy is what drives every process in the universe. It's why heat flows from hot to cold. It's why time seems to flow in one direction. It's why we remember the past, but not the future. The arrow of time itself appears to be a consequence of entropy increase. The laws of physics, at their most fundamental level, are almost entirely time-symmetric. They work just as well running backward as forward. An equation describing two particles colliding looks exactly the same whether you play it forward or backward. There's nothing in the fundamental laws that says time must flow in one direction, and yet it does. We experience time as moving from past to future, never the reverse. We remember yesterday but not tomorrow. We can influence the future but not the past. This asymmetry, this directionality of time, appears to come from the second law of thermodynamics. The universe began in a state of very low entropy. Every moment since, entropy has increased. This increase defines the direction of time. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past because memory formation requires a low entropy starting point. We can influence the future because causation operates in the direction of entropy increase. If the universe had started in a state of maximum entropy, there would be no arrow of time. Nothing would happen. Nothing could happen. The universe would be in equilibrium from the very beginning, and it would remain in equilibrium forever. So the boundaries we've explored tonight are not independent. They're connected. The speed of light defines the structure of causality. Causality gives the universe logical consistency. Quantum uncertainty sets the resolution limit of reality. And thermodynamics sets the ultimate direction and final fate of everything. Together, these boundaries define the cage we live in, and it is a cage. Make no mistake about that. We cannot travel faster than light. We cannot violate causality. We cannot know everything about the quantum world. We cannot see beyond our cosmic horizon. We cannot escape the slow march of entropy toward heat death. These are walls that no technology, no intelligence, no civilization, no matter how advanced, can ever breach. But here's what makes this story remarkable rather than depressing. Everything we are, everything we have ever known, everything we have ever loved, every beautiful thing we have ever created or witnessed, all of it arose within these walls. Not despite these boundaries, but because of them. Quantum uncertainty gives atoms their structure, which gives matter its properties, which makes chemistry possible, which makes life possible. The speed of light gives the universe its causal structure, which makes prediction possible, which makes science possible, which makes understanding possible. Thermodynamics gives time its direction, which makes memory possible, which makes experience possible, which makes consciousness possible. The cage is real, but what has grown inside it is extraordinary. Out of quantum blur and relativistic geometry and thermodynamic decay, the universe has produced stars and planets and oceans and forests and music and mathematics and love. It has produced beings who can look at the walls of their prison and understand why those walls exist. Beings who can measure the speed of light, map the cosmic horizons, probe the quantum uncertainty, and calculate the heat death of the universe, and then go home and hold someone's hand and watch the sunset. The universe has boundaries that cannot be crossed. But within those boundaries, it has built everything that matters. And perhaps that's the deepest lesson of all. The limits are not obstacles to meaning. They are the architecture that makes meaning possible. Without them, there would be no structure, no causality, no atoms, no stars, no time, no life. The boundaries are not the enemy. They are the foundation. And we, fragile and temporary as we are, standing on a small planet orbiting an ordinary star in one galaxy among trillions, peering out at a universe that is slowly and inexorably winding down, we are the universe's way of knowing that it has walls, and of finding beauty within them,